Okay, I'm back. It's been about a week. So I said last time that it was the last time I was doing another boring system update, but I wasn't reaching the performance goal I wanted when I was testing on my shittier laptop. It turns out that my computer was carrying my shitty code, right? What I wanted to do was have, maybe like 1,000 or 2,000 agents all at once performing at a relatively high frame rate. And I can get that, I can get like a solid 200 FPS on my PC, or I was able to. But then on my laptop, excuse me, my worst laptop was getting like 30. Okay. And so it wasn't what I wanted. And so I was talking about it with some other friends of mine. And they put me on this idea of making a flow field as opposed to a generic pathfinding solution. So I'm going to talk a little bit about what a flow field is. I'm not going to talk too much about the code, but rather just the process of solving for one and what that means as compared to what I was doing. So I guess the first thing I'm going to do is I drew up a representation of this level, right? And I'm going to go ahead and show that off. And so here is the level at hand, right? And so what my original solution was that every single one of these, let me swap to a different color. Every single one of these tiles, right, in my original solution would get a node, right? So let me just dot all these. Right, they all have a pathing node in them. And these actually still maintain existence in my new solution, but they're just used as a part of the solver for my initial solution. And so what I was doing was I was just optimizing really aggressively the algorithm for solving a path, right? So an agent would spawn, there's some randomization in my heuristic, right? But an agent would spawn and it would say, okay, let's just walk, and it would, develop a path between nodes. It would return a list of nodes to each agent, and they would get the path to where they want to go, and then that would happen, n times, right? So maybe this agent would go this way, because it's random, etc. Right? So all these agents, they'd get their own path, and that the pathfinding became really quickly. It was like 40 ticks to look for a path. But the problem is that not only one, this bloated every agent, right? Every agent was holding its own path on it, right? And so one thing I wanted to do for that was maybe cache a set of 20 paths at a time and just use that. Each agent pulls from a path. But then if they recalculate, let's say the map changes and the agent is here on its pathing, right? Up here. Um, if its pathing were to change, those pre-calculated paths don't work for it. It still has to calculate its own, new path again, right? And so that just didn't really work for me. And so I was talking with a friend about it, and we came up. Well, we didn't even come up with this, but this is an idea we'd heard of in the past. Is called a flow field, right? And so you're doing a similar type of pathfinding, but instead, what you're saying is essentially rather than solving for a path between 2 points, you're solving for where each possible node would go or could go to get to a point, right? And so the way that solution ends up working is you're doing a Dijkstra's or A star type look back, right? It's not A stars. I guess it's just Dijkstra's because there's no heuristic. You don't need to guess well since you have to solve every path, right? And so you do that by starting at each endpoint and walking back, right? And you keep exploring. So you'd get here, right? Let's say you start at this goal here, right? Well, how do we go here? Let's take a look at all the goals neighbors, right? So that means this neighbor could go here to get there. As you walk back, this one would go here. And then, well, these two would go here, here. Or I guess not here. It would be there, there, you know, there. And so as I'm walking back and drawing these arrows, you'll see that for each solution, so for each endpoint, I guess is what I'm trying to say, there's about uh, a lot of ways to get there. And so I'm not going to draw them all up nicely, but the point is that you get these arrows, right, for each possible path that you could take, right? Um, that's probably enough of an example right there. I'll just put that as a double arrow. That's good for now, right? And so you get these directions, right? As after you solve every node, you get these directions that say, well, this node, if you want to get to a goal, should flow this way, right? And so there's a little bit of intelligence there, right? So we're never going to have these up arrows here. They actually won't exist in the final solution. It'll end up just be saying, hey, go to the goal, right? But the point is that for each of these, you do these drawings, right? And so then the solution leads to be that each agent only really has to know which flow node it's in, right? So each of these squares has a flow node attached to it. So if an agent spawns here, it knows that the move it could take is just forward. If it's an agent here, it knows, well, it could go left or right to get closer to a node. You never want it to walk in the wrong direction entirely. And so there's a bit of randomization and choice there, probabilities. If an agent is here, right? And so this changes two things. One, agent paths are never ever recomputed. You compute this flow field at every step, but you never recompute paths, right? Each agent just exists in a flow field and it'll flow like a liquid almost the way that the flow field wants it to go, right? So, you know, anytime the map changes, these arrows recompute, but the agents stay where they are. They know what their flow node is, and they will continue to flow on that flow node. And so this actually, it realistically removes a lot of computation, as we're never ever recomputing paths. We compute once for the entire grid, and so that is one big computation, as opposed to every time something changes, 1,000 also kind of big computations. But the ASR makes it a little faster because it's heuristically optimized. But point withstanding that this is better, right? And this also solves for another thing that I was doing, which is I need to know if the player ever decides to, you know, let's say they block off a path, right? They put a block here and they put a block here. There's no way to get to the endpoint. Now, since I have a flow field, that actually solves for knowing that, because when you reevaluate, if there is no flow on these spawning points, right? If this spawn point here has 0 flow attached to it, then it was never reached. So the no endpoint could reach that starting point. And so that also optimizes that away. And so that's a little bit of a look at what it looks like. So I'll show it now in sort of in the engine here, and then I'll talk a little bit about the code, right? But you'll see here, you'll see those same arrows, right? I'm rendering the same arrows here. There's no agents. But like if we look at it from a grid point of view, right? You see here that each of these arrows has a way to go for each of these tiles, right? So this tile here says an agent on this tile will either go upwards or to the left. And an agent here will always go upwards. And they sort of flow into this point here, and then they go down. And so this does lead to be that some paths are just never going to happen. And it's because as I'm solving for it, I never add a path to an area that makes it take longer. There's only equidistant paths here. Going left or up is equidistant from the end. Going left or up is equidistant from the end, because you still have to go either left up or up left, right? It's equidistant. So we never get these really stupid paths, right, where you could flow in the wrong direction. I might still make it possible to do, well, I don't know. Anyways, I was going to say that I might make it possible to do slightly longer paths, but I don't know. That seems sort of a waste here. But you see these arrows, like the ones I drew in the example, they look a little differently. I didn't draw them exactly how the algorithm would have, but the point is that there's these flow fields, and that each agent adheres only to the rules of the flow field rather than the rules of the pathfinding that it would have to compute for itself. Right? And so if I throw, where's my agent service? Let me throw, I don't know, we'll do 250 agents at it. If we do 250 agents, you'll see that they, oh, I guess it probably didn't refresh. Yeah, 250. Let me refresh here to make sure it actually pulls that change in. I don't know why Linux seems to fail that every time, but you'll see here all these agents as they're flowing. I have them moving pretty slowly right now. They will make random choices, but they always adhere to that path. You see, they never ever have to recompute anything. So we're getting 300 FPS on 250 agents existing, right? And so these nodes, they recompute, and I'm gonna hopefully not have any issues with this. I don't even know if I tested this, but let me add a player to the scene. Where did that player go? Did I add that? No, I didn't. Player, here, you're in the scene. We'll be up to 1, 1, -2. So the player doesn't interact with the pathing, so we need something that changes to interact with the pathing. So we'll have 1, 1. We'll do 1, right? And so you'll see here, this cube interacts with the pathing enough. Oh, actually, I don't like that position. Let me move it here for the example. So this cube will interact with the pathing. Every time I move it, we'll have to recompute. You'll see that the arrows here are already vastly different. And if I push this cube, the arrows change. Now they have the choice of, I guess, exclusively going down. And every time I push this arrow, you'll see things recompute. See, now these agents are forced to walk backwards because there's no way in through where they're going. I'll even open the path for these guys to flow in. And so it's almost like, I guess I don't know what the FPS I'm recording at is, but it's 300 FPS. It looks choppy in OBS when I look at it, but I guess that's just how it is. Let me undo that so I can I guess there's not really a way for me to get it out of here. Anyways, point is that it's extremely fast, and it's the better part of it is that it's one computation. And now when I do my next optimization to make, instead of 1,000 agents fast, I want 10,000 agents to be fast. I'm going to turn every one of these agents into data, and I'll handle the rendering on my own as opposed to throwing it at Unity, right? Because what ends up, the things that actually slow down my game now are all the native calls, right? So moving each of these is slower than the pathfinding. I have to move 250 agents every single frame, and then every single frame, those agents are then passed off to the renderer to be drawn one by one. And so I'm going to have a system that batches them and renders that batch at one single pass, and it also moves everything in one pass, right? And so now, instead of each agent holding a path, it's going to hold an integer that represents where it's at in the flow graph. It'll hold like some basic data for rendering it, like what sprite it is, maybe if it was an animated thing, which it will be in the future, which animation state it's in. And then it will sort of just handle all that at once, right? Because now the slowest thing in this simulation is just all the native Unity calls. Transforms, rendering, everything there is what's actually making this not, 1,000 FPS. Because drawing, I mean, at 250, it's really not that huge of a deal, right? But drawing 250 cubes moving around, it's not intense anymore for modern computers, but it can surely be a lot less intense once it's optimized. And so that is the result of drinking beers with a friend who also makes games, who has heard about FlowFields before. And I said, oh, that's so cool to just solve every possible path on a graph as opposed to solving each path individually. Now they all sort of just flow like a liquid, right? And that's what I want. The end goal is for cool effects to exist in my game where like every tower will be AoE, everything will have a pierce cap, right? And so you'll have like this liquid mass of goblins flowing in, and you'll shoot a fireball at it, and you'll blow a hole in it, and then it'll slowly refill with the other goblins until you've either killed every goblin or the horde has overwhelmed you. That is the goal. And so I wanted to show this off. I didn't want to ramble too much about it. I'll go over a little bit of how the code works, but it's not that important. It's also the same as I showed you, right? And so if you take a look at my FlowField solver here, it's doing a lot of what the same things I did when I optimized my pathfinding, which is I cache a lot of things on the class, right? So all these things are cached. I guess I can make them read-only according to VS Code, and the reason they're allowed to be read-only is because they're non-GC hitting. Nothing here is ever resized, right? All these things stay basically the same throughout the entire run, including the count of nodes, since I'm pre-setting the size of the graph to be the size of the full level. Right, and so all these things never reset on the GC, so it's GC friendly too. And I'll eventually make this code in some public repo because I want to share this because it's maybe useful to somebody. So I have this huge set of cached things in this like scratch field that I use to never reset things, but rather, just send it back as data from an existing array. And so I pass in the entire set of every graph node, and I pass in all the goals. And then the first thing I do is I visit and compute a cost for each node, right? And so a cost is in my game, since everything is uniform, right? Let me Control Z all this shit away. Since cost is uniform in my game, the way it works is cost is simply the number of tiles it is away from a goal. So these here will be 0 cost because they are touching a goal, and then 1, and then 2, and then 3, 3, 4, 4, 5, 5, and it's always the minimum, right? So like 2, 3, 4, 5, 5. So this was either going to be 6 or 5, but it's 5 in this scenario. 6, 7, 6, 7, 8, 9, 10, etc., right? And so once I compute that grid of costs, you'll see that the next thing I do is I then create this flow field, right? So I have I have a set of flow nodes that represents the flow field. All those nodes know is where they are and where their neighbors are, right? And the neighbors are determined by our probability set, right? And there's only a max of 4 neighbors in my game, so that's preset at a size. But the point is that once I compute all those costs, I say, okay, based on those costs, so let's say we start here, right? You're always going to flow towards a lower or equal cost, right? And so this node here, once the cost is computed, it'll flow only this way, right? This one will flow only this way. This one can go to either 3, right? This one's here. This one's always going to go here. This one will always go here. 4, 3, and then 6, 5, right? And so you'll see that they always flow to a lower cost or the goal that they're heading towards, right? And so you'll see that this looks very accurate to what the nodes look like in the game, right? Where you see that you have these only flowing towards lesser value. So it'll never flow to a higher cost node. And so that's how it sort of just knows where to go, right? And so, yeah, I think this is very cool for grid-based games and pathfinding. I've never done anything like this before. I'm sure it's useful for similar games to what I'm making. If you're handling all movements on a grid, things like this could happen. I don't know entirely how I would handle it on like a hexagonal grid, right? I'm sure the computation's the same, but it's computations are. Uh, I don't. That was a terrible drawing. I'm sure the computation's the same, but like for games like this, you obviously have. It's not exactly like it's not representable by a 2D array, right? The convenient thing about square tiles or even cube tiles is that it's an array, right? With hex, I don't know, like going up 1 or down 1 in the array, that might not actually be a consistent movement direction. But I digress. That's not something that I'm working on, but I think tile-based games can all use something like this if you're trying to make marginally optimized agents, right? Especially if you're trying to go for a huge lot of them. And so I'll make another video once I get the rendering trick down because I'm stealing that from a game called, I think it's like We Are Many or They Are Many, where they have 10,000 plus agents that are like just ECS entities where they're just holding data, their rendering and their movement and everything is batched, right? To make it extremely fast. And that's what I'm going to hopefully do, and I'll be able to show off finally a humongous horde of enemies. And then after that horde is done, I will actually make towers. Not that I haven't already made towers, but this was probably a bigger change. So, anyways, this is the second to last boring video. I just walked back on my previous last boring video. This is the second to last one. No more boring shit beyond this. Hopefully, or beyond the next video. And then I'll finally have I'll have some cool videos of me blowing a hole straight through a horde of 10,000 goblins, and it'll be relatively performant, I imagine. I don't know. I don't know how that'll handle. I'll have to arbitrarily, like whenever I get this all optimized and done, I'll have to set a limit on the number of actual agents. I think 1,000 will actually be good, but the fact that I'll be able to handle 10,000 is just like good to make sure the performance is good. That I'm only at 1/10 of the max like decent capacity of my game. Anyways, appreciate anyone who watched. This is I don't know if I made it entirely correctly, but this is just sort of what I was working on yesterday to get this in. And I think it looks really cool. It's really fast. Fast compared to 250 agents all computing paths at once. They just flow, right? So anyways, appreciate anyone who made it this far. Sorry about another boring video. Eventually, a cool display to be shown. Not yet, though. All right. Appreciate it. Thank you.